So in case of failure due to longitudinal pressure force caused by the internal fluid of the pressure vessel, so fluid is inside providing pressure force, uh, actually providing force due to internal pressure. That's what we are calling by, we are uh, talking about by the term pressure force. So the force that is caused by the internal pressure of the fluid which is inside of the cylindrical vessel. Now this is actually the front view. So this end is basically the cylindrical, circular cross section. So this force due to the fluid pressure will be equal to P, and the internal dia is small d. So the diameter will be pi d square by 4 P into the area on which this P is working. Now this force is getting resisted by the resistance force inside the material on this surface. So we can say the resistance force can be written as, if the stress is sigma 2, longitudinal stress is sigma 2, and the area, this hatched area, that is pi d, which is the periphery, into t. So this is the area, and sigma 2 is the stress caused in the material. So in the limiting case, in the limiting case where the stress is maximum, if this pressure get increased by a very small amount, then it cannot be the failure cannot be resisted and failure will occur. So in limiting case means where the force due to fluid pressure and the resistance force occurred due to the property of the material are equal. So then we can find out the maximum value of this longitudinal stress. In that case, we can write P into pi d square by 4 is equal to sigma 2 into pi d into t. So here we can find out that sigma 2 will be equal to Pd by 40, okay, which is actually half of the circumferential stress. So this is the expression. So we can write, if there is no joint, then longitudinal stress is equal to half, or simply write half of a circumferential stress or hoop stress. Okay, now if there is joint, if there is a joint, that joint should be circumferential. So the joint will look like this. This will be a lap joint and a rivet joint. Generally, riveted lap joint is used. So in this case, when there is a joint, and in case of longitudinal joint, the joint will look like this. Riveted lap joint. So in case of circumferential joint, this equation can be rewritten as PD by 40 into efficiency eta of circumferential joint. So in that case, our new formula with joint will be this one. So now if we consider any particular point on this cylindrical pressure vessel, so at any point in the material of the cylindrical shell, there was two principal stress. One is this one, I mean without joint, that can be considered. Joint is some special case. So with without joint, this will be one of the principal stress, and this will be another principal stress. So due to this principal stress, there will be shear stress on the material. So these two stresses are perpendicular to each other and both are tensile. So at any point in the material, the stress setup will be look like this, and because of that there will be shear stress, and that maximum shear stress on the material we have already found out in principal stress chapter. So the maximum shear stress tau max, if you remember, that was the radius of the Morse cycle. So we can write sigma 1 minus sigma 2 by 2. So this can be written as, by putting the values of sigma 1 and sigma 2, Pd by 2t minus Pd by 40 by 2. So Pd by 40 by 2 again, so Pd by 80. So that is the maximum shear stress on the material of the pressure vessel. Now, when we have found our maximum shear stress, and if there is any joint, then here this eta will be provided, and if the eta is known, then we can find out what will be the shear stress, what is the maximum shear stress. Now we will solve a problem. We will solve a problem. Okay, the problem is a boiler is subjected to an internal steam pressure of 2 Newton per millimeter square. Okay, a boiler is subjected to an internal steam pressure of 2 Newton per millimeter square. So let us write, we have a boiler of internal pressure 2 Newton per millimeter square. The thickness of the boiler plate is 2 centimeter. Okay, thickness is 2 centimeter. Now, and permissible tensile stress is 120 Newton per millimeter square. So stress that can be maximum on the material is 120 Newton per millimeter square. We already know that in case of pressure vessels, cylindrical pressure vessels, the maximum stress generated is due to the circumferential stress, that is the maximum stress. So Pd by 2t will be equal to 120 Newton per millimeter square, that is the maximum. However, let us continue. Find out the maximum diameter when the efficiency of the longitudinal joint is 90%. So it is given longitudinal joint is efficiency is 90%. Okay, eta L is 90%, and that of circumferential joint is 40%, and our job is to find out the maximum dia. So basically D max we have to find out. Okay, this is how we will formulate the problem. Here we will write given data. So now, so we can understand 90% means 0.90 and 40% means 0.40. Okay, now we all know that the maximum stress occurs uh, in the circumferential stress. So the circumferential stress formula sigma 1 can be written as PD by 2T into eta L, because the longitudinal joint comes into play in case of circumferential stress, where if you put the values, sigma 1 should be 120, P value is 2 Newton per millimeter square. This is also given 120 Newton per millimeter square. So D will keep in millimeter. 2 by eta L is 0.9 and T is given 2 centimeter. 2 centimeter means you have to convert it into millimeter. So you write here 20 into eta L is 0.90. So from here, putting the values from here, you can find out D is equal to it will become 2160 millimeter, but we will convert it into centimeter. Okay, so as the thickness is given in centimeter, that's why we are keeping the internal diameter in centimeter. However, if you find out the answer in millimeter, that will be of no problem. But to provide similarity with the problem, we are keeping it in centimeter. Now the max diameter for longitudinal stress is given by what is the question? Find out the maximum dia. Okay, so this is the problem. Now if the problem is, if we take longitudinal stress as maximum, then what happens? Why we are choosing this sigma 1, why we are not choosing sigma 2? Very simple, let us find out. If we use the sigma 2 as maximum, then what is the problem? So in this case, this longitudinal stress will be 120, P is 2, the thickness is 20 millimeter, this is this is the formula is 40, I forgot, formula is 40, this is also 4, and eta C is 0.4. Now putting this value, we will find out, need to calculate. It will become D will become 192 centimeter. Okay, so becomes 192 centimeter. Now we have two values in our hand. So the problem is, if we take D is equal to 216, in this case, let us find out what sigma 2 would have been. If maximum stress is taken 120, in case of this one, let us find out uh, what will be the corresponding longitudinal stress, PD by 40 into eta L. Okay, so in this case, P is given 2, D is 2160, we have to convert it into millimeter. 4 into T, T is 2 centimeter means 20, and eta L, sorry, this will not be eta L, this is case of longitudinal stress, so this will be eta C, just like this formula. So this here will be 0.4. So now solving it out, we will get, let me get the calculator, 2 into 2160, 20, this becomes 135 Newton per millimeter square. So we cannot use D equal to 216, because if we use D equal to 216, then this stress over here coming out as 135 Newton per mm square. Now you may ask a question, that sir, you told sigma 1 should be maximum and sigma 2 comes minimum. So why here sigma 1 when taken 120, sigma 2 is taken 135? So how this become varied? The answer is, there is a joint, and the joint efficiency here is 90% and here is 40%. So this reduction of the efficiency in case of circumferential joint, reducing the uh, maximum value of longitudinal, maximum value of circumferential stress. Now this is why we cannot use it, because if we do that, the stress, longitudinal stress on the material will become 135 Newton per millimeter square, but the maximum stress is provided this here 120 Newton per millimeter square. So this diameter, maximum diameter cannot be 216 centimeter. So the diameter should be max internal dia of boiler should be 192 centimeter. Okay, is the problem clear? We will proceed to another problem. There are only these two formulas, and two types, with joint and without joint. Okay, I don't think there is a need of solving another problem, because the formula is very simple. Always you have to use the same formula. Now so we will not solve the problem, it is very easy. If you face problems, you can ask later on, we will discuss on it if required. So now we will go to our next topic. If the vessel is of sphere type, So now we will discuss, previously we have discussed uh, on cylinders. Previously we have discussed on cylinders. Now we will go to spheres. So let us have the vessel of spherical shell. Spherical shell. So when the spherical shell fails, there is only one type because it is similar in all the directions. So let us have a sphere like this. Now the failure will be like this. So in here will be internal pressure, say that is P, and that pressure will be supported by the material on this hatched section. The stress will be of course type of tensile stress. Tensile stress. So if the stress generated is sigma 1 and the internal pressure is P, so internal pressure P, okay. So stress is sigma 1, internal pressure is P, internal dia is small d, okay. So the area on which this pressure is working is just this one. So here this area is pi d square by 4. So the force tries to split the cell due to internal pressure of fluid can be written as pressure into the area on which this P is working, that will be pi d square by 4. Now this area which is resisting this force is equal to pi d into T. So this circumferential stress or hoop stress is only can be found here. So the hoop stress or circumferential stress, if sigma 1 just like we have written there, then sigma, then this um, resistance force will be equal to sigma 1 into where this is working in this solid region where there is material. So the area working in pi d is its periphery into T is the thickness. So this is the resistance force. So now in limiting case, this resistance force should be equal to the pressure force. So now in case of limiting situation, we can write P into pi d square by 4 would be equal to sigma 1 into pi d into t. So from here we can find out sigma 1 is equal to Pd by 40. Now along which direction they get split, or they have the tendency to split or fail, the stress generated will be Pd by 40. This is of course tensile in nature. Now if you assume, or you want to find out the stress if the failures occurs right angle to it, this is the case. Okay, initially failure occurred like this, horizontally say, and this is now right angle to it. So in this case also will be similar of this one. So sigma 2 will be pi d by 40. You see both cases are similar. Internal pressure working in every direction with same magnitude. So this will be also the hoop stress, and it will be equal to Pd by 40. So each of the material, each point of the material will face two perpendicular and same value tensile stress, both of are Pd by 40. Okay, so with this chapter we have uh, concluded the module 2. Module 1 and module 2 only we have finished. Now we will reach to module 3. So in case of cylindrical vessels, only one formula to be remembered. And if there is any joint with efficiency eta, then the stress will be found out by the formula Pd by 40 into eta. So this is how we can find out the stress, hoop stress. On problem eta value will be given, otherwise we have to find out. If eta is required and not given, in that case you have to assume any value like 80% or 85%, and you have to write, let us assume eta is equal to 85%. If required, not always. So now if thick cylinders or spheres are to be considered, then the stress distribution are not same, and the stresses on the inside surface and stress on the outside surface are different. That is not in the syllabus, so we will not discuss it. And to strengthen the thin cylinders, sometimes wire is used in a coil type over this surface of the cylinders. That is called wire wounding of the cylindrical pressure vessels. Wire wounding. Wire wounding is done to increase the strength of the pressure vessels, and that we will study if it is done in the other section, otherwise not. So I will take uh, some news in the other section what is they are doing. If they does the winding, then we will also do that. It is like if this is the cylindrical pressure vessel, winding is done. This way to improve the strength. This way this winding is done. So in that case, what happens is the hoop stress is being supported by the material of the cylindrical pressure vessel itself plus these wires also. So here the wire supports more stress. This is sigma c supported by the material, and also we have these wires, and that wire takes the stress sigma w. Okay, now this is not we are going to do right now. I will the syllabus written on this topic is very less. It is not clear to me, so I will ask RM sir who teaches in the he teaches, then I will also teach. So it will uh, let's okay. Now now we will solve another chapter, that is the third module, which is the deflection of beams. Let us have a new page. Deflection of beam. This is the third module. The whole chapter is on deflection of beam, so you must pay attention, and your options will be very less over here because whole module is on deflection of beam. Now, if a beam carries uniformly distributed load or a point load, the beam will be deflected from the original position. And in this chapter, we'll study the amount by which a beam is deflected from its position. Due to the loads acting on the beam, it will be subjected to bending moment. So what will happen is whatever the beam, we just consider one, a simply supported one. Now, if any load is provided there, any type of load, the beam will face bending moment and deflect. And deflect, if we magnify the deflection, let us magnify the deflection. It will look like this. Okay, so the weight, there will be some type of weight, and due to that weight there will be bending moment m. So we know that the bending moment formula Video got freezed the first time. It will come back very soon. Okay, it is okay now. So due to the loading on any beam, there will be bending moment. Now if there is the beam get deflection, like the figure, the radius of the curvature can be found out by the formula we have found out from our simple bending or pure bending equation. M by I is equal to E by R. So from here we can find out that R will be equal to I into E by M. So here for any beam I will be constant. If the material is homogeneous, then E will also be constant. Now the R to be constant, the M has to be constant. So the radius of curvature will be constant if M is constant. So that means the beam will take radial shape with the radius of curvature as capital R only when the bending moment M is constant. So the beam when loaded, if this IE by M is constant, the beam will bend in a circular arc. So in that case, if we consider our study, suppose we have a beam AB. Okay, now that AB takes the shape like this. So if this is C point, this will be C dash, and we can say that this bar has made an angle theta at A, and this can be named as O, the center of curvature. So this is D. Okay, so if this angle is theta, this angle will be also theta. Now the radius AO or BO will be R. Now, so initially the beam was ACB. After loading, it has become AC dot B. Okay, the R is then radius of curvature. Y is say CC dash or deflection at center of the beam. Okay, here CC dash is say Y. Now I is of course the moment of inertia of the beam. E is Young's modulus. Theta is the angle made by the tangent at A with the beam. So theta can be written as slope of the beam at end A. Okay. So in this scenario, Okay, time is up. It is 48. Um, let me check at once if we have 5 minutes or not. Okay, we have 5 minutes only. We have 5 minutes only. So let us check. So in this case, we know that tan theta will be equal to theta when theta should be in radian. And now for a practical beam, this will be very less. Please do not cause this disturbance. Okay, so tan theta will be theta when theta is in radian and also very less. So in any practical beam, this deflection will be very less and this theta will be also very less. So in that case, when theta is very less and in radian, then we can write tan theta is equal to theta. So if we ignore the directions, we can write this tan theta will be equal to dy dx. So we can write dy dx equal to tan theta is equal to theta. Now again, from here we can write AC is equal to BC is equal to L by 2. Now from the geometry of the circle, from the geometry of the circle, we can write AC into CB is equal to DC into CC dash. We have learned probably in class 10 how this happens. L by 2 into L by 2 AC into CB is equal to 2R minus Y into Y from this figure. This is 2R DC dash 2R minus Y. So it will be DC. So now the equation can be written as L square by 4 is equal to 2R into Y minus Y square. As we have said, for any practical beam, Y is very less. So Y square can be neglected. And from here it is written that Y is L square by 8R, where Y square is neglected. Why? Square of small quantity. Okay. Now we remember Y equal to L square by 8R. We will put the value on this bending equation. Bending equation is M by I is equal to E by R. Here we will put the value of R. So from here also we can find out R is equal to E into I by M. So now we have found out Y equal to L square by 8R. So there in place of R we will write E into I by M. Okay, just we have found out in previous page. Now here, from here we can write then Y is equal to M L square by 8 EI. So this gives the central deflection. So this is actually the central deflection of a beam which bends in a circular arc. And from triangle AOC we'll write sin theta equal to AC by AO is equal to L by 2 by R, that will be L by 2R. So now sin theta is equal to theta if theta is very small. Now then we can write theta is equal to L by 2R. We just